Okay. So before I go on to a bunch, the actual topic for the day, there's one interesting bit that I talked about in previous weeks, but I didn't actually go and show it any. And it was about how we know that the electrons are the things moving in the current. Right? Is that we couldn't figure that out from electrostatics or from electric current directly. We needed something else, and now we have something else. We have that when we have current in a magnetic field, it matters, right? Because our force, y'all can, yeah, it's getting focused, okay. Our force is going to look like QV sine theta. And this has a sign. It's either positive or negative. So the force changes whether it's an electron or a proton or any other positive or negative particle. So we can imagine a circuit, and we're going to draw this circuit in, and it's going to be a battery. And then we're going to pass current like this. And then in the middle, this is going to be sort of a resistor, but it's going to be a big object, a big flat white object. And it's going to look like this three-dimensional shape that I'm not very good at drawing. It'll look like that. All right. And so we have two choices. The electrons can go from the negative pole of the battery through the circuit, or conventional current can go from the positive pole. All right, so it's either a positive or a negative charge. And I'm stating it as, all right, this is going to be I minus and this will be I plus. We don't know which one of them is true yet, because in the case of everything else that's going on, it amounts to effectively the same thing. Right? This circuit works, whatever it is. Now, a weird question would be, what happens if I pick a point here A and a point here B, and ask what delta V, which is VA minus VB, is? With nothing else going on, this has to be zero. And I'll put a little question mark beside it there, because it's the same point on the conductor, right? It's the point at the same potential on the conductor. If this is a resistor, we're going to make sure to put it at where VA equals VB, right? So, if we have a resistor and it's a big resistor for some reason, we'll adjust it so that this has to be true. Now, this thing, now what we're going to do is put a magnetic field under it. And it's going to go through the material and out. And so if this is our positive current, like this, we can do the right-hand rule to determine what's going to happen to this current. All right, we have the current going down the page or out of the page, and the field is up. And so a positive charge will go to the right. So what should happen is this current should veer off to one side, which means this side will get a positive charge and this side will get a negative charge. Now, what will happen is, on the whole, this accumulation of charge will build up an electric field across the material. And so the electric force will balance out the magnetic force, and you'll come up with a stable voltage. No new charge will go there, because any charge extra that goes through here will feel an equal magnetic and electric force, and it just goes through. So you just get a buildup. And so here, you get to you have what's called the Hall voltage. A guy named Hall figured this out, that if you have a current flowing, in this case, you get a positive Hall voltage measured from A to B. So now I'm going to draw this again. And now we're going to consider what happens to the electrons in this case. If the electrons are flowing, what happens? All right, so this is going to be I minus, and we're going to have the same, all right, so there's going to be a thickness here, and there's going to be the same magnetic field. All right. So in this case, the current is going into the page, and the magnetic field is up. And so a positive charge would be pushed to the right. And then we remember that negative charges feel the opposite force to positive charges. So you would get a magnetic force on negative charges to the left. And so you get an accumulation of electrons on the left and the deficit of electrons on the right. So now this is less than zero, because the voltage has to go from positive to negative to be positive, right? But we're measuring from A to B. Right? There's a B, and those points should normally be zero, but because we put in the magnetic field, it pushed charges to the edges of this thing, and that is dependent upon what charges are flowing. All right, if you have positive charges flowing, they're going to flow from positive of the battery to negative, and so you get the accumulation on the left. If you have electrons flowing, they have to flow from negative to positive, and you get the accumulation of charges on the right. And this is easy to do. You take a meter and you poke it on your material and you say, I get a negative voltage. Electrons must be flowing. And that's what happens. And this is kind of a, stepping through it a step at a time, it makes sense, but it's kind of seeing that it should make sense, starting from this circuit and being like, oh, that could depend on which way the charges flow, isn't obvious. That's not the only way we know, right? If you're skeptical of this, there's other things that we know, right? When we build semiconductors like transistors and advanced logic stuff, we have to know what thing is moving when we design it. And we've designed all our stuff based on electrons moving, and it works. For that matter, we build sensors using this effect. Most of your phones, if they can detect magnetic fields, and if they have a magnetometer inside, they probably have a small sensor that does this measurement. And most modern things now do something like this rather than have a big coil of wire. And I'm going to explain why this is easier, because you can make it small. Nothing in here matters on the size of this thing. All right, maybe if you have the charges too close together, then you get too big of a compensatory electric field, and so you don't get a big voltage measurement that you're expecting. Maybe maybe there's a size matter there, but in general, you can make this thing really small. You can always just pass more current and adjust the magnetic field if you're trying to control it or adjust. You can adjust the circuit to measure whatever magnetic field you want. Anyway. All right, so that's like the last thing. That's the thing it depends on current flows and magnetic fields. Now we got to go do this other stuff. I want to share screen. I want to share the slideshow. I want to hide controls. All right. So the last week was we have a current flowing and it generates a magnetic field. And we also have, just calculating forces directly on charges due to magnetic fields. What we wanted to get into is, where does the magnetic field come from? Right. So we talked about that. We talked about a current flowing generates a magnetic field, or a charge moving will generate a magnetic field. It's easier to calculate for a current moving. But when we talked about current before, we talked about it in the context of Ohm's law. Right? Is you have some potential difference somewhere. You have a battery or a capacitor or an arrangement of electric charge. And the current will flow from high potential to low potential, or conventional current will. Right? So if a magnetic field can cause a current flow, then it must also cause the electric potential, or we should be able to associate an electric potential with the magnetic field that causes the flow of current. Slides won't advance. There we go. And so we know magnetic fields can cause currents because we can do things like make a coil and bring a bar magnet into it, and we'll see a voltage across the coil. We'll actually measure this potential difference that we're talking about, which means that we know current is flowing. We can measure the current directly. And we can just set up an experiment like this with meters and coils and magnets. And this is how it was discovered. Except there's one thing. It's not the presence of the magnetic field. All right, you can set it up and just leave a magnet in a coil or near a coil, and it does nothing. Turns out that what matters is when the magnetic field changes. That's the important bit. And so what we say is that the current that ends up flowing is induced. The motion of the field, the change in the field, causes a change in the current. And so because we need, these slides use the term EMF, electromotive force. That's the thing I've been calling potential difference. Because you always need an EMF to cause a current, the coil has an EMF across it, what's called the induced EMF. Now, in your mind, think voltage. This is just, there's a voltage on the coil because we've stuck a magnet next to it and moved it. So there's a few different ways of generating, but there's a few different ways of changing the magnetic field in a coil. One is we can change the size of the coil. If we stretch the coil out, then there's more magnetic field lines going through it. We've increased the flux. And if you remember, I talked about flux for a bit in electric fields, and that was confusing because I told y'all to imagine arbitrary surfaces. Here, it's the shape of the coil, right? You can understand if the coil gets bigger or smaller, or if it rotates, if the coil is not aligned with the field so that less field lines go through it. Right. So we can cause the field by changing the size of the coil. We can change the orientation of the coil, or we can change the magnetic field directly. Whatever's causing it, If it's a permanent magnet, we bring it closer, pull it away. Or if it's a current, we increase or decrease the current. All right, so for a current to flow, there has to be a complete circuit. So the current flows when we measure it. If there's no circuit for it to flow through, then there's just an EMF, but there's nowhere for the current to go. So one of the examples we're going to look at is looking at changing the area. And this is a weird sort of thing where we're going to set up a problem of a conductor moving through a magnetic field. So I'm going to start drawing on the slides now, if I can. All right. So So if you can hear me on the Zoom call, apparently I'm still recording. How is that? The power went off to the computer. And then I come back and it's still running. I don't know how. So PowerPoint has locked up on me. So it's going to be a little weird. I'm trying to get it to do what I want to do. Here's the Zoom call. It says it's recording. And I'm going to share. Just share the screen. There we go. If for some reason the recording isn't working, which it should be, then I'll make sure you get a different version of this that makes sense, because I have last year's and the high school version. And like I told the people in person, the Hall effect stuff at the very beginning is not on the test. It's just stuff that you should know. Like you should know how transistors work at some point, because they're just everywhere. You don't need to know all the details or anything or work stuff out with it though. So we're talking about magnetic fields causing currents and causing voltages, causing EMFs. And we're getting into this example, which I was going to draw on. And I think this is what caused everything to go all to crap. I don't actually want to show that slide. I don't want to show this slide. So there's a velocity of this rod. It's going to be moving through a magnetic field. If you take a piece of rebar, any sort of magnet, it's not magnet, any sort of iron or metal, and you just wave it around in a magnetic field, this will happen to it. Because you're moving it around, the charges are moving around. Now, in a material, the nucleuses are generally going to be bound in place mostly. In the metals, the electrons are very free to move. They're conductors. And so what you're going to get, if you look at doing right-hand rule on this, your charge is to the right of the screen, your velocity is to the right of the screen, and your field is into the screen. So you will get positive charges being pushed upwards and negative charges being pushed downwards. The right-hand rule tells you what the positive charge does. So the charges that can move experience a force and are pushed to one end of the rod. Now what this does is it looks very narrow, but this is a capacitor, which means there is an electric field now from positive to negative. And we're going to ignore that for a moment. While we're moving the charges around, the conventional current is up while we're setting up this potential difference. So this is what's going on is we've taken the battery out of the circuit and we replaced it with this moving rod. But by our actions, moving it through the magnetic field, we're doing the work that the chemical reaction would do in the battery to cause a potential difference. So what's going to happen is your current flows if you can set up a circuit using it. So this is a rod moving on rails. Then it would flow around the circuit to go from positive to negative back. All right. The thing is, normally you would expect it just to go through the rod or along the electric field, but it can't do that because we've caused a current to flow in the other direction. We're generating the electric field. And so we have to give it another way to move, and it does. It follows the rest of the circuit around. So by moving the metal in a magnetic field, we're generating what's called motional EMF. It just means that there's a potential difference here. All right, there is delta V because we have this electric field generated. So we can calculate what that will be. At the moment, we're just going to tell you what it is. But I'm going to use this to I'm going to explain it later when we tell you the more general case. All right, and so what's going on here is you have this squiggle, which really is delta V. That's a Greek squiggle. I don't even know which one it is, but it's representative of the electromotive force of EMF. And it's the velocity times field times the length of the rod that's moving. Because that's the thing, is that the thing that's moving is this bar. That's the only thing that can experience the magnetic field. So its length has to be important. So briefly here, all right, we have that the velocity is going to be the distance it moves over time. All right, so this distance is going to be our delta x. All right, so we can put that in. So delta x times L, delta t times b. All right, so delta x times L, right? We have a box in essential that is like this. So this bit is the change in area over time times b. What we've done is we've set up a loop. It has one turn. It goes through the bar, through the conducting rails, through the light, everything else. And now we've stretched it out. We've increased the area. And that increase in area causes more field lines, more magnetic flux to go through the loop of the circuit. And that's what causes the EMF. All right, so we have an example here. If you take a copper rod and you move it around in a magnetic field at a particular speed, right, we can ask what the voltage is on it. Right? And so we just got, it's one equation, plug and chug. If you can recognize from the problem that it's a motional EMF, it's a bar of metal moving in a magnetic field, then you can calculate it. So if you took a copper pipe that long and you moved it at a fairly slow speed in a high magnetic field, I get that this is 0.29. And then we go and we look at our units. A Tesla here is a Newton per Coulomb divided by a meter per second. So the meters per second will cancel out. And then we have Newton times meter per Coulomb. That is joules per Coulomb. That is volts. So this thing is 0.29 volts. Units work out. I keep, every once in a while I'll be like, oh, the units work out. The point of that is in physics, sometimes we can just make combinations of the units and it gives us an idea of what might be the some new thing that we want to understand. Don't know what's going on outside. Like there's a tent.
Oh, I think they're, like yesterday they had something for the freshmen, and I think today they're doing some sophomore event, and then tomorrow juniors.
Oh, that's fun. Okay. Just wondering. All right. Oh, this was already calculated out, and I did all. I forgot. There's some of these where I haven't done the calculation on them. All right. So, all right. So, we give this a different name. We call it EMF instead of potential difference or voltage. But I want to be clear that it's a voltage. It works in circuits like a battery. We can do Ohm's law and do the power law with it. If we couldn't do that, all of modern society would fall apart because we wouldn't have any electricity aside from whatever we had from batteries. And battery tech would probably not have advanced the way it did. So we can put in a light bulb and ask what is the current that flows due to this EMF through the circuit. Now, I want to be clear is that when we apply Ohm's law here, the resistor acts as a limiter to the current flowing. Is that this is not a coil producing current independently, freely. It's a coil producing current, and that current goes and is used somewhere. So other ways you might calculate the current, you can't go back and be like, oh, the current should be this value and it's too big. Right? There's a difference between a loaded coil and a coil that's unloaded, which means a coil with a resistor and a coil with that's just connected up. So it's always find the voltage, find the EMF, and then use it in the circumstance that's appropriate. So the wires, the rails have no resistance, the bar has no resistance, but the light does. So we're going to do V is IR eventually, but this V now is this funny EMF. So we have magnetic field B, we have a velocity V, we have L, all right, and so our EMF should be VBL, and that is 5 meters per second times 0.8 Tesla times 1.6 meters. This is, I'm doing all my calculations on my phone. 0.8, 1.6, 6.4 volts. And then we can do I is V over R is 6.4 volts over 96 ohms, which is 0.067 amps, or 67 milliamps. The idea is that if we have a voltage in a problem, we can use it in Ohm's law if we have a circuit. And in this case, we had a circuit and we found the current. So we can also do things like find the power, right? It's going to be V squared over R. So 6.4 squared divided by, 6.4 squared divided by 96. This is going to be about 0.4 watts, right? To move this bar through the magnetic field, it's going to generate about half a watt of power. Where does it come from? Yeah, it comes from you doing some work, which means there's something else going on. So here's the calculation for it. All right. There's a current flowing through the bar in a magnetic field. Right. So if we do right-hand rule on the current, right, current is up, field is into the screen, your force should be to the left of the screen. there's a force in the opposite direction to the velocity. Once you push the bar, it tries to resist the motion. So you do work against the resistive force that's generated, and that work is what pushes the current around.
And as soon as you stop it, that force goes away, right?
Yeah.
Okay.
So the idea is that it resists you. If you stop pushing, the bar would come to a stop.
Yeah.
All right. The circuit's whole design is without a source of energy, it comes to a stop. Is if the current naturally flowed, the bar would, say the bar shifted a little bit for some reason naturally. The electrons in it drifted to the right. Then it would be pushed upwards a little bit. That would cause the electrons to drift left from this resistive force. The bar wants to stay stationary. You have to do work to move it. Excuse me. All right. So I think that's the next slide. Is you have to provide the energy moving the bar. So you have to provide a force that balances the magnetic force on the current. That's where the energy comes from. It's not free in any sense. And you can calculate what that force is. It's just the force, on the current is ILB. All right, so another question. You have a conducting rod. It's going to move through a magnetic field as it falls. And it's going to fall between two rails so that it's trapped, it's constrained to fall in one orientation. All right. Now, no current flows in this case. All right. But what's going to happen is, as this thing falls, your velocity is downwards, your field is askew to the right. That's going to cause voltage to build up on the two rails. And so that means there's a resistor hooked up across it in the second picture. Does that second picture fall just as fast as the first one, or slower or faster? So here, what we're noticing, this W here is not the velocity. It is weight is mass times G. It is a force. So here, there is a weight force, and then there is a magnetic force. This is F is ILB. So if you push, all right, so in the first picture, the bar clearly accelerates. There's only one force on it, it's gravity. It accelerates downwards, which means the electric potential, the EMF is a function of time, which is V of time times B times L. All right. So the potential grows as the bar falls. In the second picture, now there's an upwards force. That means it has to accelerate slower. So it's going to fall slower anyway. And what's going to happen is it's going to come to a point, right? You can calculate the acceleration is F minus M, sorry, not F, erase that. So it's the magnetic force, so ILB minus mg over the mass. All right, that's going to be your acceleration. It's going to reach a point where these forces are equal. The acceleration is zero, the velocity is constant. Right. Imagine this is drag. This is a parachutist falls out of an airplane. They pull their chute. While they're free falling, it's the first picture. Once the chute opens, they're going to slow down to terminal velocity with the chute open. And the force from the air upwards is going to hold them up there's going to be no new acceleration. Right. So it's obviously going to fall slower, and it's going to come to some limiting speed. Okay, that's fun. This is what I was talking about the area changing, right? Is remember, E equals BBL was really changing area over time times B times L. Nope, L's not there. All right, that was from a previous slide. If you change the area of the circuit, then you have this force generated. And I keep talking about the magnetic flux. Now we define what it is. Magnetic flux is the field times area. And really, it is the definition that you saw with the electric flux. This was EA cosine phi. So the magnetic flux is BA cosine phi. And if you could define a field for things, you could define a flux for it. It has to be a field with magnitude and direction, like electric or magnetic fields. So you have wind speed. You know, if you have the velocity of the wind outside has a magnitude and a direction, you could define, say, how much wind is hitting Muse Hall, and that is a flux of wind. All right, so you can, we're using the term flux broadly here, but you're just imagining field lines going through a surface. And of course, we give this definition when B is perpendicular to A, but for the arbitrary case, you're going to have the cosine phi component. And of course, the angle is defined here. When you have an area, it doesn't have an orientable distance normally. And so what we do is we define a vector that's perpendicular to it. There's two of them, one up, one down. We pick one. Generally, if there's an inside and an outside, we pick outside. And then if it's something like this, then we pick it so phi here is going to be less than 90 degrees. All right, so we have this normal. In this case, because of the cosine, it doesn't matter. But it might matter if it was inside or outside. Current loops will never be inside or outside. They'll be just one side or the other. So it'll always look like this. But this gives us the normal, which just means perpendicular, means we have one direction that we can say, this is the orientation of the area. And then we have this. So, but what this does is if you have a surface, if this is your area and your magnetic field is like this, then this flux is 0. By the way, this symbol that's typed here, it looks like the angle symbol. One's lowercase, one's capital. I'm doing this mostly for people who's going to reference this later if they re-watch the video or something. And this is what I mean is you can have a set field and a set area for your coil, but the orientation will change how much of the field goes through the coil. How are we on time? Yeah, I got plenty of time, but I mean, I would like to stop at a particular spot in the slides. So again, magnetic flux is just the number of field lines passing through the surface. And now it's a real surface. It's the area bounded by the coil. All right, so we're going to do this problem and then we're going to call it a day for today. So this is describing it's a description of a possible motor or a possible generator, I guess, right, is actually, we might go a few more slides, but there'll be a slide. I'll say that's it because I don't want to do extra, I want to stop at a particular point. So the solenoid part is telling you about the magnetic field. So if we go back to last week, you notice solenoid. The magnetic field for a solenoid is mu naught, lowercase n, times the current in that. This is the solenoid. And then in here is this 12,000 turns per meter. And then mu naught's a constant. So we can calculate what that is directly. 4 pi times 10 to the minus 7 Tesla meter amp, 12,000 per meter. Turns per meter is a counting, that you're counting the number of turns. So it's units is per meter. And then you have 5 amps, and then you'll get a field. So I get 0.075 Tesla out of this. Check, we have 10 to the minus 6, 10 to the minus 4 is 10 to the minus 2, 10 to the minus 1. Yeah, it's getting pretty close. That's close to 0.1, so our numbers are okay. So we have a magnetic field. Now we can draw that in. Here's our magnetic field. We have a current loop, which will be like this. It has a radius here, so the area is pi r squared. And it's going to rotate from 20 degrees to 80 degrees, right? So if this is our loop, right, our angle is going to go from something like that. So our angle phi is 60 degrees. All right, let me stop here for a second. All right, so there's our previous slide. The point of this is we're going to set up what we're trying to do. So let me go back a second to here. This was our equation that we're trying to get to. Go the wrong way. There we go. Right, so we have B, we have A, right? So our flux is going to be B, A, cosine phi, right? So our change in flux is going to be change in the flux over change in time. The field is constant. It's caused by something else. And the area is constant because the coil is rotating. It's not stretching. And so it's going to be BA cosine phi final minus cosine phi initial. And so we can calculate that. Our magnetic field was 0.075 Tesla. Our area is going to be 0.005 meters squared times pi is 7.885 times 10 to the minus 5 meters squared. Wow, that went bad. And then this thing in parentheses, well, the cosine of 80 degrees is 0.17, and the cosine of 20 degrees is unknown at the moment. 0.939. So when we subtract those, we're going to get a negative number. So what I get is 4.5 times 10 to the minus 6. And then we got to go through and do units. All we have here is Tesla and meters squared. That's the units for the flux. That is only the change in flux. I ought to be careful of this. Change in flux over time is a different thing. You have to divide by the time. That's just a change in flux. We don't know if it takes a week to rotate or a day or a minute or 3 microseconds. But that's the total change in flux. All right. So that's a lot of calculating, right? You have to draw your orientations out, figure out what's going on, where you start, where you end up, and translate what's the field, what's the area. And there's no reason why you couldn't go back and do problems like this with field and area and calculate the change in flux. But once you notice the type of problem, it's easier to change it. So this is the thing, is if you have a coil and it experiences a change in flux, you can calculate the EMF, the voltage coming out of it. So the minus sign pops up. All right, we're just stating what it is. We're not proving it. The minus sign pops up because of the behavior of the coil later on. But obviously, if you have N loops, each loop experiences the same change in flux. And so it'll contribute its own bit to the EMF, and so it adds up. And then, we're always going to do calculations like this, and the flux is always going to be a cosine phi. And so there's 3 ways the flux can change. You can change the size of the field, you can change the area, or you can rotate the coil so that phi changes. Yeah, this E here should be a curly E, but and remember, this is just delta V. Anywhere where you have this EMF, you can put it in for voltage, for potential difference. So you can make circuits using a coil in a magnetic field. And we're going to do that. I mean, when you see that lab eventually, which is probably in a couple weeks, it'll be circuits built out of coils. Good. Yeah, this is the slide I want to stop on. So actually using this. All right. So coil of wire, 20 turns is N. And the coil has an area, so we're not going to calculate it, thank goodness. And the field is perpendicular to the surface. Perpendicular means phi is 0, right? Because our drawing is going to be, here's our area, our coil. Let me erase that. I don't like that. Here's our magnetic field. So that's E. And then our area vector is going to be perpendicular to the coil. So B is parallel to A when the field's perpendicular to the coil. And so this means that cosine 0 is 1. Y'all see that? I wrote it off the side of the screen. That's crap. So cosine phi is 1. All right. And then we have initially and then finally a magnetic field. And this occurs over some time. Right, so this is delta t. So our EMF is minus n delta phi over delta t. And then it's going to be phi final minus phi initial. So phi final is B initial. Phi final is B final area, and then cosine phi being 1, the cosine phi goes away, and phi initial is B initial times area. So this is, this will be minus NA B initial, or B final minus B initial over T. And so we do that calculation. All right, cosine 0 is 1. We have N and we have A, and then we do the B final minus B initial. And what we get is a coil like this, a reasonable magnetic field. This is quite larger than the Earth's magnetic field. You get about 3 millivolts. And so that's all well and good, but what that generally means is if you're trying to generate EMF of significant size, like let's say I wanted to reproduce the 120 volts coming out of the wall. That means I need either a high magnetic field, or I need a large area coil that can shrink and change. That's really hard to engineer. Or I need tons and tons and tons of coils. That's reasonable. We can just do a lot of wire. Or I need this cosine phi to switch between plus and minus 1 as fast as it can, which means high rotation speeds. And that's what we tend to do is we have a reasonably sized coil with a lot of turns, and we spin it as fast as we can. That's how electric generators will eventually work. There'll be more about that in the next couple of slides, but this is about where I want to stop, but I will talk about this. Induction stoves, they're a thing now. They weren't a thing when I grew up, but how an induction stove works is you've got some source of magnetic field in the stove. Generally, it's a big coil of wire, and it's running on house current, which is alternating, so it changes direction all the time. So the magnetic field changes, and you have two pots, a glass pot and an iron pot, let's say. The glass pot, clearly, there's no circuit, right? There's no way current's going to flow through an insulator like that. But the iron pot, there's no reason why electrons couldn't flow in a circle around it. So it does. That's what happens is the magnetic field going through the pot is going to push current through the pot. Now, no conductor is a perfect conductor. So this is a circuit that has its resistance basically all along the loop of current that's flowing, which means that there's a power loss, which is I squared R. We don't know what I is, we don't know what R is, but we can deduce it from the rate at which the water boils. Right, because that energy turns to, we're taking the energy that's used to push the electrons through the iron pot, and that's essentially heat. We're making it heat and using it to boil the water.
But wouldn't some of that go to the water and some of it go to the electron?
What do you mean?
Like, if there's some of the energy would go into the water, and then a different amount of energy would be
Oh yeah.
carried by the electrons being pushed up.
Oh yeah, the electrons would have kinetic energy. That's fine. The pot gets hot as well, and the pot being hot is the electrons and the molecules in the pot moving. It has thermal energy. Right? Yeah, it's not dumping a bunch of, but that is it is as it warms up, the whole system can't really get any hotter than the water, because the water is going to boil off and it's going to draw heat out of the pot. So, right. So that is that you're inducing current flow, and the whole point is to waste it. The whole point is to turn it as much of it as possible into heat. And so if the pot has electrons moving at higher speeds, so if they have energy, well, that's heat as well. It's just heat that will get to the water later.
So does the glass pot not work?
Yeah, the glass pot doesn't, the electrons don't flow, don't move through the glass because it's an insulator. And so that's why all these induction stoves are basically glass tops, or something of plastic, or it's got to be something that's resistant to heat. So it's usually glass with stuff underneath it to do the current flow to generate the magnetic field, and it induces the current in the pot where the current can flow.
So like electrons aren't coming out of the stove into the pot. It's just the magnetic field moving around the electrons already in.
Yes.
Okay.
Yes. I will, on Thursday, I will try to have examples of what's going on here, because there's no reason why you can't do this with permanent magnets. When you go home, if you have a neodymium magnet at home, take it like an aluminum cookie sheet, if you have one of those, or just some large non-ferromagnetic material, and let one slide across the other, and you'll feel a resistance. And what's going on is, no matter the material, the magnetic field, or the fact that it's trying to slide, will cause a current loop in the metal. Generally, you have a problem with that because you use iron and then it just sticks. So that's why I say aluminum, or maybe you have a copper bottomed pot. Maybe that. Pennies are good. You can move a penny across the top of a big magnet, and you'll feel resistance like it's in molasses. And I'll try to show that in particular next time. I gotta go get the stuff and bring it, but it's a demo worth doing, so I'll do that. This is where I want to stop, so that's it. Everyone left the Zoom call suddenly. That's weird.